These are the notes for LT3 and the energy unit. And this is mainly a conceptual learning target. There's not super fancy math calculations, but our task is to analyze the transformation between potential and kinetic energy in simple mechanical systems. Now, the big word here is mechanical. Think about a mechanical pencil. Mechanical pencil, you got to click something. There's moving parts. All right, so when you see the word mechanical, it just means in a system where there's things moving, like in a roller coaster. All right, it doesn't have to be anything super fancy. So one of the first things we're going to do, all right, we've already discussed in previous targets what potential and kinetic energy are, but we're going to talk about now these two in terms of what is called mechanical energy. Okay, when you see the word mechanical energy, just think of it as the sum of those two. So it's the potential energy and the kinetic energy. Sometimes you'll see this as TME, which is total mechanical energy. All right, in some of the simulations and the worksheets that we use. No need to write this down, but just kind of take a peek at it. And if this is a roller coaster, and after I drew this, that is one heck of a steep hill right there. But if we've got a roller coaster going up this hill, we've talked multiple times about the fact that potential energy would be at the top of the hill. It might even stop moving a little bit right before it comes down. So if there's 15,000 joules of potential energy there, we should already have an idea that as we come down the hill, we're going to go faster. That's just common sense. And we're getting closer to the ground. So we're going to see this value decrease. And this value, if we ignored friction, we said there was zero friction on this roller coaster, not possible, but we can pretend, we would know that this kinetic energy at this point has to be exactly 15,000. Because as this goes down, this kinetic energy would increase. So we will always see these two values have an inverse relationship. So are inversely proportional. So potential and kinetic energy are inversely proportional. Now some of the times, we're going to overgeneralize a little bit, but potential energy, the way it gets that is they consider it stored energy. Okay, it's stored energy. And a lot of times in this unit, we're talking about gravitational potential energy. Okay, so this is gravitational, which means it has a height above the ground. But there's all kinds of potential energy. There's chemical potential energy, which we've mentioned before, like in gasoline and food and batteries. There's elastic potential energy. Maybe you're shooting archery, you draw the bow back. Okay, there's elasticity there. The arrow has not done anything yet, but if you release, you know that the arrow will take on kinetic energy. So this elastic potential will be converted to kinetic. All right, so when we talk potential energy in this equation, we're really talking gravitational potential energy. But keep in mind for later on and future targets that potential energy can take multiple forms. Think back to the pendulum gizmo. All right, and hopefully you recall it because you know how awesome my drawing skills are not. And let's say that this is ground level. Okay, so that thing's just going to swoop by the ground. And here's an imaginary spot, and over here is an imaginary spot. All right, so we've got this pendulum, and let's just say we've got case A, B, and C. If I told you that at A, I'm just going to pick a random number here, it has 250 joules of energy, we would know if that's as high as it goes, that is all potential energy. And so we could also say then, well, as it swoops by the ground, maybe it's cruising this way at first, that we've lost our potential energy, but we never really lose it. It just gets transformed into something else. So at B here, we could say, well, there's still 250 joules of energy. It's just that now it's kinetic energy. And then as we keep going through here, if we're ignoring air drag and friction, at C, Still 250 joules, but we're back to potential. So the kicker is, what would we say, how could we figure out, what about these mid-marks? Okay, somewhere along the way. Because we have a total of 250 here, a total of 250 there, a total of 250 there. So we have to have the same total. Our total mechanical energy has to be 250 joules. And so here we know, well, it's above the ground and it's moving, and it looks like it's halfway. So if our PE plus KE, potential plus kinetic, has to equal 250 joules, and we're halfway between there, then this must have been 125, and this must have been 125 to get our 250. All right, because it'll be extremely important to remember that total mechanical energy stays constant. Okay, our total mechanical energy always stays constant.